Okay, open your eyes and let the world in. Follow me on a journey into your body's second most complex organ after the brain. But pay attention now, all of this will happen in the blink of an eye. First job at hand, get inside. Let's follow this dust particle. It floats up and lands on the cornea. That's the outer dome covering your eye. You can feel its shape right now. Close your lids, put your index finger over them, wash your hands first, and move your eyes side to side. Feel that bump? That's it. No blood vessels here. Your corneas get oxygen directly from the air, so your eyes breathe. But it's full of super sensitive nerves. They sense something foreign, and the fastest muscles in your body get to work. Your eye blinks. That dust particle gets washed away. Let's try this again. The only way to get into the eye is with light. That's how your vision works, and it's why you can't see in the dark. Duh. But how do we see objects that don't emit light themselves? The light coming from the source, be it a light bulb or the sun, hits the object. Some of it gets absorbed, and some of it bounces off and enters our eye. It's a nice reflection on you. More on that a bit later. For now, it's way too dark in this room. Somebody flip a switch. Ah, that's better. We zoom along, going the speed of light, and pass through the cornea. It's dome-shaped to help focus light where it goes next, the lens. But before we get there, we pass through the pupil. It's not a black circle in your eyeball, it's a hole. Black because there's no light inside your eye. Red eye in flash photos is because the light from the camera is passing through and bouncing off the back of your eye. It's full of blood vessels in there, so your pupils glow red. But this pupil's too small, I can barely squeeze through. Ow, the light's too bright. The tiny muscles in your irises, that's the colored part of your eye we know and admire, have relaxed to make the pupil smaller. This doesn't let too much light in and protects your eyes from excessive brightness. Turn the lights down a little, and the iris muscles contract. The pupil gets bigger as the eye demands more light to be let through. There we go. We pass through and come upon the aspirin-sized lens. Like your ears and nose, your lens continues to grow throughout your whole life. And just like in a camera, it focuses the light even more. That way, it hits exactly where it needs to be on the retina. That's the back of the eye. I can see our human here is nearsighted. Things far away are blurry. Look at where the lens is focusing the light into a single point. It's not on the retina, but a little before it. This happens when your eye is slightly too long. If you're farsighted, things up close are blurry. That focal point goes behind the eye because your eyeball's too short. Don't worry, it's nothing a pair of glasses can't fix. Ooh, it's roomier in here than I thought. Hello? Well, it's because you only see about 1/6 of your eye when you look in the mirror. The rest of it is inside your head. Your eyes themselves are about the size of ping pong balls. And just within this seemingly small little organ, there are over 2 million working parts. Whoa, hold on. Everything's shifting to the right. Whoa, now to the left. Our human must be looking for something. Your eyes move thanks to 6 muscles holding them in the socket. Certain ones contract, and your glance changes direction. Up, down, left, right, all around. Okay, things have calmed down, so let's continue following the light projection. Say you're looking at a big bright apple sitting on a blue table. A yellow light bulb hangs above. If you could see the image in here, it'd be upside down on the back screen of your eye. It's because the lens bent the beam. But you can't see this picture on the retina because eyes aren't projectors. It's just light hitting some tissue on the back wall of your eyeball. There are nerves and special receptors back there. They turn the light coming into your eye into nerve impulses the brain then decodes and makes sense of. So, we journey further. Here are those receptors. They can be cones or rods. Cones are the reason your incredible eye can detect up to 7 million colors. Surprisingly though, your cones come in only 3 types: red, green, and blue. It's the combination of their work that allows you to see magenta, chartreuse, or cyan. Except for colorblind people. They might be missing one of those types, or they don't work as they should. So these people don't see certain colors at all, or things aren't true to their color. For example, if there's something wrong with your green-sensitive cones, green and yellow look reddish-brown. There are also your rods. They pick up black, white, and over 500 shades of gray in between. Way more than 50 shades of gray. You also have more of them than cones, and the rods are mostly in charge of your peripherals. Yep, everything outside your direct field of vision looks like old black and white TV. Rods also help you see in low light. The photoreceptors in your eyes are so sensitive, they can even project an image when it's not even there. Ever looked at a bright light, closed your eyes or turn off the light, and you can still see the shape of that light bulb floating before your eyes? That's your photoreceptors continuing to send visual information to your brain. Your rods and cones are connected to neurons, so the data gets passed there and makes its way to your optic nerve. This is where blood vessels and the main path to the brain enter and exit the eyeball. This is also where your blind spot is. There are no rods or cones here. You can test it too. Grab a piece of paper and a pen. I'll wait. Okay, make a dot on the left side and a plus about a hand's length to the right of it. Hold the paper at arm's length, close your right eye, and stare at the plus sign. The dot will disappear because it's in your blind spot. If it doesn't, move the paper closer or further away until the dot disappears. Do the same thing with your left eye closed and stare at the dot with your right eye. The plus sign will vanish when it enters your blind spot. You don't notice these spots because your brain fills in the missing information. So, we travel along the optic nerve and into the message decoder, your brain. Ow! Shocked me. Oh yeah, we're in the nervous system now. So, we're traveling with electric impulses. The optic nerve leads into your brain's visual cortex. This is where that upside-down image gets translated into something we understand. That's a blue table with a red apple sitting on it. A yellow light shines above. And your brain knows up and down thanks to your ears. Well, your balance system, which is mostly in your ears. Anyway, the brain is also where missing puzzle pieces, like the stuff in your blind spot, gets filled in with information based on its vast collection of archives. The dot on the left is my blind spot, so I'll just fill in the missing space and make it look like the paper continues seamlessly there. But our journey didn't start when we entered the eye with light. It started when light from a source bounced off an object and then into the eye. Why do we see different colors? Because visible light travels in different wavelengths. That red apple on the table absorbs other colors and reflects red-white waves, also pronounced as red light waves. The table reflects blue and so on. Black objects absorb all the light, and white things reflect most of it. Those reflected waves hit cones and rods sensitive to them, and your world is filled with color, especially red-white waves.